test 11. Almost there, right? One more after this. That's it. It's all about fluids. All about fluids. In 12.2, we spoke a lot about fluids that were not moving. And in 12.3, the fluids themselves were moving. That's the major difference in these two sections. 12.2 was a lot lengthier, though, than 12.3. 12.3, you noticed there was very little math involved. It was rather simple math, AV equals AV. But 12.2, there was a lot more math involved. So let's start with 12.2. The first thing that we learned was about density. Now, we learned specifically about what we call mass density. But the phrase density in general means what again? What does density really mean? It's a general phrase, not about mass and volume. But what is density really? How could you describe it in other words? Okay.
The amount of mass in the space.
That's mass density. Volume, but again, still mass density. Amount of mass in a certain volume or space is mass density. But what did I say in class? I talked about this. Generally, what's another word for density, or what else could we say to describe it? The what? I wouldn't use the word thick, but I see what you mean, Matt. But I wouldn't use that word thick, because you could have an object that's thick that's like styrofoam, and it's not dense.
Hardness.
Not hardness.
Concentration.
Concentration, that was the word I used. It doesn't have to be that word, but the idea is that you can have a concentrated amount of whatever in a given space. So you could say that the density of students, or the concentration of students in the room we talked about, if you pile a lot more students in here, would be a lot greater. Or you could even say something as simple as how many of you are in art, or AP art, or in some sort of art right now? Okay. AP art's next year?
Yeah.
Okay. So usually this is an AP art technique. Have you done drawing with dots only yet?
No.
It's really kind of cool. So two of my friends I grew up with now to this day are actually, they're not artists, but on the side they do a lot of design work, like freelance design work. And one of them, one time I remember we were sitting there, I forget where we were somewhere, and all he had was like a ballpoint pen. And he was sitting there just using dots, literally like this. And with enough dots, he actually ended up making like a person's face, and you could see the mouth, the eyes, and he made the dot intensity greater or less in certain areas. That's a great example of density. Right now, these dots are really close, but if I went like this, that would be a low concentration or a low density of dots per unit area. So density doesn't actually always mean mass density. Is that clear what we're saying here? And I want you guys to understand that density is really just concentration. That's a low concentration. That's a higher concentration. Could have done it there, actually. So the idea with those dots is what we're talking about. So mass and volume, units of mass are kilograms, units of volume are meters cubed. Usually volume is drawn like this for the V if it helps. Not to be confused with lowercase v for velocity, which we will use in this chapter also. So we got units of kilograms per cubic meters. Where was density used? Give me an application where we use density in this chapter. Come up, yeah. Okay, an ice cube in water. The ice cube is less dense than the water, so ice cubes traditionally float. Okay, that works. That works. Where do we use it specifically in here? We talked about the difference between floating and sinking, right? That was the big key that we used density for. So let's compare those two. We did this in class. I'm gonna quickly go through them. We're gonna get right into a problem because this is stuff that you should really know already. Okay, we have two options here: sink and float. If an object sinks, what do you know about its density compared to the density of the fluid it's contained in? It's more dense. And then if it floats, obviously, yeah. Okay, if you're less dense than water, you float on water. If you're less dense than salt water, like the Dead Sea we talked about, you definitely float on salt water. Okay, because your density is less than that of the salt water. We did the egg example. That's a great example to reference to what we did in class where the egg floats or sinks. So it starts off sunk. The egg is more dense than the water. You pile salt into the water, which increases the density of the water, and therefore the egg is no longer more dense than the water. It starts to float. And that was the simple demo we did. When an object, God bless you, when an object floats, what do we know about it as far as forces are concerned? Travis?
The force of gravity is less than or equal to the buoyant force.
So in this case, very good. We know that gravity does not overcome the buoyant force. So for now, let's just say equal. For now, let's say equal. But yeah, Travers makes a good point. The buoyant force could be greater than that actually, and it would shoot out of the water, but then it would land back on the water. So when I say float, let's assume it's at rest, floating on top of the surface or at the top. Okay, so those would be equivalent to each other because it's not moving at all. Now, when the object has sunk though, why does it sink? I know, yeah, the object is more dense than water, it sinks. But force is reasoning. For the answer with force is why does it sink?
Because like the force of gravity pushes it all the way down, and buoyancy doesn't even it up to go back up.
Correct. So if our free body diagram here, gravity or the weight is greater than the buoyant force. That's the only time something's going to sink. If that's not the case, you're not going to sink. You might be somewhere in between sinking and floating and be like levitating in the water there. That's a different story. But if it sinks, you know that the weight has to be more than the buoyant force. But when it's floating, we know that these two things are equal to each other. So the vector arrows are about the same length now. Okay, we drew free body diagrams all year. Don't forget about them, please. It's very useful here. I can guarantee you that tomorrow you will have to draw, Monday you have to draw a free body diagram. Okay, so be used to doing this. Clearly greater than this, these are equivalent to each other. Now, there's another thing we talked about. We talked about a phrase. The phrase was called apparent weight. The apparent weight of an object. What does that mean? What are we referring to when we talk about the apparent weight of an object? Not the weight of the object, but its apparent weight. Apparent weight. We're talking about fluids.
What it's immersed in fluid.
Yeah, when it's immersed in a fluid. Think about when you go in the water. Do you feel like you weigh 100 and whatever much pounds you weigh normally? No. You feel like you weigh less than that. A little bit less. Maybe not much, maybe a lot less. If you're in salt water, what do you feel like you weigh? Pretty much nothing, like heavily salted water, right? So something with a heavy density in the fluid, you pretty much are at balance. If I subtract Fg and Fb over here on the right side, right? If I subtract these two, what do I get? 0. My apparent weight would be 0 from floating. Well, if I want to figure out what my apparent weight is normally, when I'm sunk, I could say F net equals Fb minus Fg. Just the difference between the two. So if my weight is normally 150 pounds, but buoyancy pushes back up with 120 pounds, I feel like I weigh 30 pounds. Okay, again, if my weight, I'll give you a mathematical number so you can see this at the bottom. If my weight is normally 150 pounds, I'm using pounds instead of newtons because I'm using common sense what we use. And the buoyant force pushing up is 120 pounds. The F net will be negative 30. This is what you will feel like. Why is the answer negative? Why do you still feel like it's a negative number? Which way is gravity? Go ahead. Because you've sunk, because you're being pulled down. Okay, look at the free body diagram. Clearly you can see that Fg is greater than Fb. Okay, Fg is greater than Fb in this problem. So Fg overcomes Fb. So the natural or net force in this case would be downward. So you'd have a negative. So you feel like you weigh 30 pounds in that case, in that scenario. Let's see. Last but not least, probably the most important part that a lot of people have been forgetting. What do we know about volumes? When an object is floating versus when an object has sunk, how do we relate our volume of the object and the volume of the actual fluid displaced? How do we relate those two? Draw yourself a picture if you need to. Mike, what do you got?
Isn't the volume of the object equal to the amount of fluid displaced?
If it has sunk or floated, Mike?
Sunk.
Yeah. When the object sinks, VF equals VO. Now, I came up with another way to explain this in the other class. Hopefully this helps, because I feel like people have been in trouble with this. Ready? So far this chapter, we've called VF volume of fluid displaced. F for fluid. Write it down if you want to. VF is just the amount of the object that's underwater. The portion that's underwater. Well, if you sink, how much of you is underwater? So, how much of it is underwater? VO, the whole object. Again, write yourself a note that think of VF as how much of the object is underwater, or under the fluid, whatever it is. VF is how much of it is submerged. If you're fully submerged, VF and VO are the same because it's fully underneath. If it's floating, it's not the same. Okay, for floating, I'm going to draw a picture so we can see this. For floating, we look at something like this. This is VF right here. Take a look at what I'm shading right here, please. This is VF. Can you actually see that? Probably not. That's the amount of the object that's underwater. That's what VF is for a floating problem. So for a floating problem, we know that VF is less than VO. VF is less than VO. Because only a fraction of this object is actually under the surface of the fluid. When a fraction of the object is submerged, it means that VF is only a part of the whole. So VF might be 7 when the whole thing is 9. So 7/9 of it is underwater or submerged. Those are two really, really important things with volume. This is usually the part that students forget, and as a result, you have trouble because you have too many variables unknown in problems. When an object sinks, you have to right off the bat write this down. Literally, right off the bat. If you're given the volume of the object, you also know VF because they're equal when it sinks. If it floats, you don't really know too much. Maybe you're solving for part of this. If you recall from class, we did an example with an iron ball bearing sitting in liquid mercury. And the question was, how much of this object is exposed out of the water? How much is exposed? I hope we're paying attention. The question then would really be presenting what's above the water right here. Right? So you take the overall object and subtract VF to get what's above the water. If you've got the overall object is 9, 7 is submerged, 2 is out of the water. And I'm not even using units, okay? Meters cubed, whatever, for volume. Questions on the theory so far. This is all theory, but this applies to the questions for math. Obviously, on the multiple choice and short answer, you have to be able to answer questions that are related to these ideas. But this helps us a lot with the mathematical component we're going to look at now. Good? Okay. So let's take a look at an example. I'm going to make it up on the fly. Let's say, well, let me ask you, I don't know if you saw it already. So let's do something, I'll change it obviously, one of the first 4. Let's say that an object sinks, okay? An object sinks under the water at a certain depth. I'm not given that depth or anything like that. I know that the volume of the object is given, and that's going to be 2 cubic meters. I can tell you that we're in salt water. Salt water has a density of 1025. Do you have to memorize that? What do you have to do? Be able to find it where? Or on the test? Yeah, on the table. It'll be a table. It's not on the formula sheet, but it'll be on a table or given in the problem. Okay? But at home, if you don't know the values, either use your textbook and find them in the table, or at least Google the value. But usually Google gives you densities in grams per cubic centimeter. So just convert that. Now, the density of the object, if it sinks, has to be what? Give me a general idea, not the answer. If it sinks, the object's density must be blank than the liquid's density or the fluid's density. It must be blank. Mike? Greater than. To sink, you got to be more dense. Okay? To sink, you got to be more dense. And think about it for a minute. Styrofoam, is that very dense? And if you put it on water, what's it going to do? It'll float nice and easy. Take a piece of metal, like a pen, like we did with this slab. When you drop it in the water, what happened to it? Because copper is more dense than water. Okay, so I don't care what the number is, but it's greater. Give me something between 1,000 and 2,000. All right, easy enough. Okay, it doesn't matter is what I'm saying, right? I'm picking arbitrary numbers right now. All I know, though, is it's got to be bigger than 1025. For this object to sink, it's got to be bigger than 1025. Okay, let's put an ocean floor so we know that it's at the bottom now. Okay, let's say it's at the bottom at least. Let's say the problem asks you several things. First, find the weight of the object. Find the buoyant force. And then find the apparent weight. do you find the weight of an object? Formula, quick. Weight of an object. The weight of an object. It should be like automatic, like instantaneous. It was like chapter 3 of the year. mg. Okay, mass times gravity. It's what we've done all year, right? Do we have mass in this problem? We don't. But we know that mass is used in another formula. What's that other formula? Density equals mass over volume. Solve for mass. Solve this for mass. Mass equals rho v. Replace rho and v right here. And then the rest carries down. So again, replace the mass of the object with rho, is the density of the object, VO, the volume of the object. Both are given in this problem. Here's the volume of the object. I didn't put an O up here earlier. I should have put an O. Here's the volume of the object. Here's the density multiplied by G. You get a number. Somebody calculate it, please, so we can press on. $1,500 times 2 times 9.81 seems reasonable. Okay, about 3,000 times 10 about 30,000. So I'm going to agree with that answer. Now, that's the weight of this object. How do I find buoyant force of the object? How do I find the buoyant force? If you don't have it memorized, where do you look? Yeah, look at your formula sheet. Come on. If you don't know this by now, you should have your formula sheet out. Open it on your iPad if you have to, or on your phone, like some of you like to do. What's the formula for buoyant force? Buoyant force equals. Buoyant force equals. Buoyant force equals. Buoyant force equals. Nobody has it memorized? Do you have it memorized? Yeah. Rho Vg. It's the density of the fluid times the volume of the fluid displaced, aka however much is submerged, times G. How much of this object is submerged? Part of it or the whole thing? The whole thing. So what's VF really just? Yeah, VF is also just 2. VF is really just 2 as well. Density of the fluid times the volume submerged times 9.81. What do we get for this number? 110?
Yeah.
0.5. Thank you. So I'm stepping you through the problem. Notice what I'm doing here? I could have jumped to part C automatically and said, what's the apparent weight? And to get the apparent weight, you would need to find the weight and the buoyant force. Follow me. Listen for a second, right? If your weight is 100 pounds and the buoyant force is 70, the apparent weight is 30. We know that we have to compare those. So I'm literally stepping you through the problem here. So when the problem gives you parts A, B, and C, try to think about the fact that A and B are probably going to affect C or vice versa, or maybe D or later on another step. Okay? So how do I find apparent weight again? What am I going to do with these two values? What am I going to do with these two values, Jack?
Use correct buoyant force on the weight.
Yeah. So we've got the buoyant force minus the weight. This will give us F net. Where does that really come from? It comes from the free body diagram. Here's FG. Here's FB. Okay, the free body diagram over here on the far right shows us that FG acts down, so it's negative. FB acts up, so it's positive. My net force better be negative so that the object stays on the ground. So 20,110.5 minus 29,430.
It's about 9,319.5. Yeah.
Props, Jack. Very good. Good, that's a man. Yeah, agree? I didn't do mine. Nice. So, this is the apparent weight. This is what it feels like. So, here's what you want to think about. Ready? How much weight did you lose when you went underwater? You started here. You're now here. How much approximately, fraction-wise? You're now a third of what you started with. So you lost how much? Around 2/3 of your weight. Literally, you feel like you weigh approximately 1/3 of what you actually weigh. of what you actually weigh.
What if you actually measure yourself underwater? Like scale.
Could you actually figure out that value? A person probably wouldn't, because humans are actually less dense than water by a little bit if you're holding in air. So you wouldn't be able to stay down on the ground. But if you blew out all the air, remember I gave that example, and they had a scale at the bottom of the ocean or floor of your pool, and you step on it, it absolutely would, as long as it's not electronic. You need like the old scales, the little spring scale on it. If you could submerge it under the water and step on it, it would measure the weight that you would be. So it would physically work. I mean, you do that for extra credit if anyone has a pool. You can get it to work, but I don't want you to break a scale. I'm actually going to give you an extra credit this period that you could do over the weekend, so it'll be bonus points for the test if you do it. Any questions on this kind of a problem? Now, remember guys, in class we did an example with floating. We did an example with something being brought to the bottom of the ocean, chained down, and then inflated. This is just the third example. There's a fourth example to look at in section 12E, those extra problems that we didn't do yesterday. We did the last four. The first four of them, one of them is a problem, actually two of them are problems like this. I highly recommend you look at those problems. Okay? So again, the stuff that we did not go over in 12E, numbers 1 and 2, were similar to this kind of a problem. After this section in 12.2, we had two other things. Those things are things that you watched on your own. The first part was this. Pressure equals force over area. So, ready? I'm standing in front of the room. I go like this, ready? I lift one foot. What have I done to the pressure? What's the answer? One word. Increased. Increased, ready? How much area am I standing on? Two shoes, the area, right? And now? So my area went, and how are they related? Okay? Indirect relationship, area goes down, pressure goes up. If your little brother jumps on your shoulders, what are you adding to yourself? Force. More weight, force, right? So by putting somebody on your shoulders, you'd also be increasing the pressure. Clear? Now, if I lay on the ground on my back, what am I doing? Increasing the area, which therefore decreases pressure. That's why when you lay down, doesn't it feel so good at the end of the night? Think about it, really, that's what you're doing. You're taking your weight of your body and displacing it over different parts of your body that can then be balanced on the floor. Plus, your muscles are usually at rest when you're laying down. When you're standing up, why are your muscles tense? Keeps you from doing what? Yeah, that's all it's doing. Theoretically, if you could lock your knees, which you really should never do, there's really not much tension in your legs until you start to move like this, and then your muscles start to resist that motion. Okay? Pressure equals force over area. Now, this was then related to Pascal's principle, which told us that the pressure in a container with a closed fluid is equal in all parts. So this was the first part is separate, right? We did that on its own, and then we went to the second part called Pascal's principle. This was the hydraulic lift, the mechanic example. So you go to the mechanic, and you have a hydraulic lift. One end of the lift will have a small cross-sectional area. The other will have a very large cross-sectional area. How many of you have gotten, everybody should raise their hand really, but have you been to the doctor and gotten a needle before? Right? When they inject you, what do? They push down on what? What is that called? Do you know the word?
Syringe.
The actual whole thing is a syringe. What's the thing they're pushing down? Plunger?
Yeah.
Not like a plunger in the toilet, but it's called a plunger. So they push down the plunger. That's actually, another word for that is a piston. A piston, like in a car, it forces things up and down. That's what's happening here. So there's a chamber of fluid, and we've talked about this already. There's a chamber of fluid inside of here. Okay, it's filled up. Then there's a little piston right here, and a piston right here. If you push down on this piston, think about it at the doctor's office, when they push down on the injection, right? It has to go somewhere, doesn't it? So where's it going to go here? Well, the fluid can't escape. So if you push down and this piston goes down, what's going to happen over here? It's going to push up. It's going to force it upward. Why is this important? It creates a what? What do we call that phrase? MA, where the letters it stood for. With a lever, it's the same thing. The lever, it's the same thing. Mechanical advantage. A mechanical advantage. And here's the theory. If the pressure is the same in the fluid throughout, then we know that this is true. If you have a smaller area on this side, you don't need much of a force. You need a very small force. A bigger area means it can lift a bigger force. So to find out your mechanical advantage, and you did these in your problem sets and in your other work already. Well, actually, maybe not the problem set yet. When you're trying to figure out the mechanical advantage, I think I told you guys, take a look at the output force over the input force. So let's say you apply 75 newtons of force. That's your input. And let's say it lifts a car that weighs 2,700 newtons. That's the output force it results in. So whatever that number turns out to be, 2,700 newtons over 75 newtons, that will give you the overall advantage. Remember, it's a factor of increase in the force that you're giving. You give some force, it increases that force by what factor? That's the mechanical advantage. It's not the difference between the two. You don't subtract them, you divide them. Okay? What would that give us? Anyone want to just give me an idea? 225 over 75 is 3. So it's going to be more than 30.
36.
What is it?
36.
36? Is that approximate or exact?
Exact.
So the mechanical advantage here is 36, coming up here in a minute, is 36 times what you put into it. Imagine that, though, for a second. Imagine you were, like, in sports, that's not the case, but imagine you throw a ball and you're able to throw it 100 miles an hour. You're going to go 3,600 miles an hour if you got an advantage of 36. It's pretty incredible to think about that, right? You're putting in very little force, yet you're generating a much, much greater force. So when you go to the mechanic, they have a hydraulic lift usually there. They put the car up on the lift, on the top there. It connects to parts of the axle or the undercarriage, and it literally lifts it up. The mechanic can slide under and look underneath the car to see if there's any problems. Okay, it's called the hydraulic lift. There's way more than just this. Okay, the channel called the hydraulic press channel, it's a press that pushes down and explodes things. You ever seen that? It uses hydraulic forces. That's the only reason it can make things explode like that. The force going down is incredible how strong it is because of hydraulics. Okay, because of hydraulics. You need to know how to do math here. If you're given the radius, can you plug it in directly? Where does it go? Where would the radius fall in? Area. You could replace this with pi r squared. You could replace this with pi r squared. If you're given the diameter, what should you probably do? Take the diameter and have it to give you the... And then go ahead and plug in. Makes it easier, okay? Makes it easier. Questions on this? This should be one of the easier math topics of this section. Okay? After this, we had this formula, which you just used a moment ago in your lab. This is absolute pressure, or I also call it the total pressure. This is atmospheric pressure. And this is gauge pressure. Gauge pressure is from the water or whatever you're submerged in. I have to put fluid because it could be a gas technically. You can get the pressure of your tires, and that's called gauge pressure. And that's the actual pressure inside. It's a gas. Is this not even, you guys can tell me. Sorry. So if you want to figure out how much the water is pressing down on you, all you're looking at is the gauge pressure. But because on top of the water or the fluid that you're in is air, air also weighs down on you and applies pressure. Here's the pressure from the air pushing down on you. 1 times 10 to the 5th on the earth. Okay, on the earth. That's your constant. Everything else we don't really know. Maybe we're figuring out capital P. Maybe we're solving for rho or G or H. Okay, but this is capital P. Another thing, by the way, you don't have to do this, but some people put a line under the P like this. Take a look at this, please. To indicate this is pressure and not rho. These look very similar, don't they? Okay, some teachers in college for me did it, but some students like to do this. Just like the V for volume is capital, for a capital P, put a horizontal line underneath here to show it's capital P. This is lowercase rho. Okay, that's the symbol for density. How could you be asked a question like this? Maybe you're asked to figure out the depth to give you a certain pressure. What would you be solving for in that case? H. Maybe you're going to be asked to find the density of the fluid. If you're given a certain depth and you know the pressure at that depth, it says, what's the fluid? You need to find the density and then find it in the table. So you'd be solving for rho. Maybe you're on an unknown planet and you know the total pressure and you can figure out the pressure under the water. You can then find the atmospheric pressure on that planet if it were a different planet. Okay? There's a lot of stuff you can determine here. Depends on what you're being asked. Okay, this is the easy portion for math. I'm not going to go over another example of this. Okay? I'm going to go into the next section. We can get through everything. In 12.2, did we end with surface tension or was that 12.3? 12.3? 2? So surface tension in 12.2 being the last thing. Can somebody explain in layman's terms what surface tension really is? What's surface tension? A fluid, obviously. Surface tension of a fluid. What does it do? What does the tension on the surface do? The what? The surface bends, good. And what does it physically do, though? What does it physically do?
I think it can hold something for a while, like support the thing.
It supports an object, okay. So it bends, and while it's bending and supporting an object,
It makes it want to get like smaller.
yeah, what it's doing really, and it's hard to see this actually. I can show you with the shirt, okay? Imagine this shirt is a surface of water, okay? And you push into the shirt. See how the shirt kind of bends like Bernadette was saying? When you do this, you push like this, by stretching the surface, by pushing, you're increasing the surface area on the surface. Surface tension wants to minimize surface area, so it naturally pushes back up. So surface tension can support the weight of something if it doesn't bend that membrane enough to go through. If I step on water and just put the tip of my toe on it, what's going to happen? The surface is going to kind of contour my toe. But as soon as I put a little bit of force, what's going to happen? I'm going to fall right through the surface because it can't support my weight. But a bug or a leaf or other small things like grass or a piece of hair, for those gentlemen that already are shaving a lot in a sink, if you fill up the sink with water and you're shaving, you keep cleaning the razor, usually the hair floats on top of the surface. Sometimes it'll sink, but it sits on top because of surface tension. That's what's happening there. The hair itself is so light in weight, it's got very, very, very little mass that the tension in the actual water can withstand and hold it, almost like normal force. Almost like normal force. Okay, think of a trampoline. I told you that was the example to think about when you're thinking about the way the water itself kind of bends. Okay, the water bends there. All right, 12.3 now. We had a couple ideas in 12.3. We talked about laminar and turbulent flow. Laminar was predictable, turbulent was unpredictable. We talked about the word viscosity. Viscosity is an object's you want to give it? Because, yeah,
Like.
without using exact words.
I was gonna say something about flow. I was gonna say like.
You can use an example like more viscous is easier or harder.
Yeah, like honey is easier than water. So like thicker stuff. I don't know, but.
You're on the right track. Thicker, viscosity, help her out.
Something with a higher viscosity has more density, so it's harder to pass through.
No, it's not always density. Keep going without the density part.
I mean, it's harder to pass through and it moves more slowly.
Yeah, the molecules do not pass by one each other as easily with a high viscous material. When something has low viscosity, it flows readily or very easily. Something with high viscosity cannot flow very nicely. Caroline asked about quicksand. She said that must have high viscosity. And we ended up looking it up. It also has to do with the actual density itself. But think about like molasses or syrup as the example, or honey, high viscosity in those materials. Now, the math parts we talked about were A1 V1 equals A2 V2. But then we also said this is really just volumetric flow rate, so this is another formula that you can use. This is given on your formula sheet, so you don't have to memorize it. The second part is not given on your formula sheet. It's not given. Look at your units. Area is meters squared, velocity is meters per second, which makes this meters cubed per second. Meters cubed is really volume, second is really time. So this second formula here, although it's not given on your formula sheet, you are still responsible for it. Okay, this is very useful, and we use this We actually used this together yesterday in class, if you recall, with the math problem for 12E. Okay? A stands for area, V stands for velocity, capital V stands for volume. What does the continuity equation really just tell me? What is it similar to from earlier in the year? What is the idea of replicate, really? Something we've seen twice already. We've seen it with energy, we've seen it with momentum. We've seen something with energy and momentum that is really related to the continuity equation. That's the word, it's in one single word. Conservation. Conservation. The flow rate cannot be changing. So if it comes through the high area, like you just saw in the lab a minute ago, and then you've got a nozzle where you put your thumb over the end of the garden hose, it's going to shoot out with much more velocity. Why is that reason? Because look, if the volumetric flow rate in the beginning, say it was 20, right? The product of these two, let's say it's 20. And now I tell you that the area goes down from what it initially was. The only way for it to still be 20 is for the velocity to go up. So area and velocity are indirectly related. Indirectly related. And last thing today, Bernoulli's principle. What does Bernoulli's principle tell me in several, one sentence you can tell me Bernoulli's principle?
As the velocity goes up, the pressure goes down.
Very good. There we go. We're done with Bernoulli's principle. Now, here's your extra credit opportunity. In the problem set, one of the questions talks about a hair dryer and like a ping pong ball or a small object, a small ball that's not very heavy. Now, if you take a hair dryer and aim it vertically upward, like girls, usually for your hair, ladies know they use hair dryers all the time. You normally aim it horizontal, right? The hair dryer. Aim it straight up, and you put a ping pong ball. It'll sit there and levitate. It's very easy to do that, actually. I don't care about that. You can do that. If you can do that alone, I'll give you 1 bonus point. If you can do that. Okay? If you can do this next part, I'll give you 2 bonus points. Well, you can't do both. The next part, you can take a hair dryer and actually hold it horizontally, a little above the horizontal, and it'll still float. Which kind of blows your mind. This way it makes sense, right? The air is pushing up, it counters the weight pushing down, it makes sense. Yet, if you hold the hair dryer, I'll draw a hair dryer. If you hold a hair dryer and you let the air fly out at an angle and hit the object, here's what's going to happen. You get really fast air flowing over the top and slower air, we have examined, slower air over the bottom. When you have a slower velocity or lower velocity, you have high pressure. When you have fast velocity, you have low pressure. If you have higher pressure below and lower pressure above, what force does that create? We have, what's the word? On a plane, we have lift. It creates a force of lift. An imbalance of pressure indicates that there must be a net force acting from the high to low pressure. This is what we talked about with Bernoulli's principle. Okay? The video. Okay, I want to see a video of you doing this. And you should really be able to explain it in the video also if you want the full 2 points. Okay, so take a video and explain it. Good.
Could you work with someone else?
This is really, really simple. If you really need to, it's fine. Sure. But I want you to both be in the video so at least I know who's in it.
Wait, so the second one is you tilt it a little bit?
So yeah, it's got to be a little bit above the horizontal. It can't be perfectly horizontal. It's got to be angled up. You got to kind of try it a lot and find the right angle. It might not work. It might, depending upon the ping pong ball also. If it's not working with a ping pong ball, feel free to start and try something a little bit smaller. Okay, that might be a little bit useful. Hey, one other thing before we get to the examine. I pointed out that this is given to you on the test. That's a formula that's given. But Pascal's principle, which relates to the hydraulic presses, is not given as a formula. So make sure you remember this, please. Okay, this top part that's circled is on the formula sheet. Pascal's principle says the pressure is the same in 2 locations. So all you're doing is using Pascal's principle and replacing P with F over N. P with F over N.